15.1 and 15.2, the common ion effect in buffers. And for the worksheet, I want you to do all the worksheet that goes with this lesson. Number 1, number 2, number 3, AB, and number 4, AB. Now, I'm looking over my notes. Well, first of all, there's one, I don't know if it's a surprise to you now, if you do or not, but when I teach this lesson, when I teach this material, we're doing chapter 15, I do 14 and 15 together in one giant lesson. So this is like the last full chapter we do. So the good thing about this chapter, if you know how to do an icebox with an Ka acid, do a Ka acid problem, find the pH and all that, icebox, or Kb, all the problem, find the icebox, pH and all that, POH, pH and all that. Well, then we add a few more steps on it, and it gets into what's called buffer or common ion. So when I made these notes a long time ago, yes, there's a lot I can condense and cut out. There's a whole lot that I didn't need to put in there, kind of repetitive. And so I'm looking at this, I'm trying to figure it out now, and I don't have my notes at school. I have my own original notes that tell me what order I teach things in and all that. But I'm looking at this right now, and I'm going to jump around a little bit, but I think you'll be able to get this. And I think I'm going to show you a couple of things in this video. It's probably going to be more than one part, like part 1, part 2. I'm going to show you a couple of things that are not going to be on the homework yet, but they'll be on later homework, just because it'll save time. You can always come back and watch this if you don't get it. Okay, so you'll see what I mean. Okay, so first of all, 15.1, the common ion effect. We have already done something a lot like this. I'll just say this for now. Let's just say that we were doing an icebox problem. Okay, and you do ice. And normally you say, okay, the original molarity or pressure or whatever we did before of A was 0.100. And then that's going to be 0, okay? And well, that will have to be something too, I guess. Let's do it the other way around. Let's just say that this was 0.100. Okay? Now I'm going crazy. I'm trying to make I could have done it that way. That would have been fine. All right, now we'll do it that way. Just because you're used to seeing it this way. So here's a chemical in equilibrium with A plus B, 0.100. Normally when you do your icebox, this is your initial for AB, and these are 0, right? Okay, you know that. You've done that a lot. Minus X, plus X, plus S, plus X, and all that. Well, what if you did not have a 0 here? What if you started off with this, and you also had an ion, A was an ion, for example, we'll say, maybe it's plus and minus, and A was like 0.05, 050. Well, that's called a common ion. And what happens is, having that initially is going to affect your equilibrium, and that makes sense. If everything is 0 to start off, then it's the way we've been doing it before. For gases, or mainly for acids and bases, is what we would look at this. Acids, bases, and KSP, or where this becomes a big issue. Normally it's all zeros. But if there is a number here, you have what's called the common ion effect. And all that means is, if I had something right here like 0.05, then I'm not going to shift as much over to the right as I would have otherwise. I mean, if I have all zeros, you can solve for equilibrium, or do this and solve for equilibrium, it's going to be different. That's going to block it a little bit. You don't need as much, to come over. So anyway, so how can I recognize a common ion effect? All right, here's the better way. I didn't give you a real definition there, but it says here, common ion effect is a shift in position of an equilibrium system caused by the presence of a species involved in the chemical reaction. Well, that doesn't sound too good either, does it? Well, here is, I'm going to do a calculation and show it to you, and I'll do this one for you. It says, calculate for A, hydrofluoric acid ionizes in water according to this equation. So HF plus water gives you H3O plus and F minus. Okay, so first it says, calculate the H plus, the pH, and the percent ionization of HF in a solution that is 1 molar HF. So if I have I'm going to have a solution. The idea was this was prepared in water. Like, say you started with pure water, you added this acid or this chemical, it might have been hydrofluoric acid, it might have been hydrogen fluoride gas even, but you add this to water, and this is what ends up occurring. Pure water. Okay, so what is the pH? All right, and it says Ka is 7.2 10 to the negative 4. I almost wouldn't do this, and if you know it so well, you can even zip past it. I even have the answers on the paper, but I'll do it really quick. So it's 0.100 molar HF. Well, I'll put it over here. 0.100 molar HF. So what is the pH? Okay, so 0.100, 0, 0, minus X plus X plus X. Sorry, I'm standing on a lot of stuff here. Remember, the floor becomes my desk with all these papers I have here. Notes for every class I do. All right. Ka expression. Okay, then assume X is negligible, of course. Am I in a good place? Yeah, can you read that okay? I guess. All right, so 7.2 10 to the negative 4 equals X squared over 0.100. Oh, I always forget to put a little approximate sign, because that just makes it a double safe to do it that way. So X, well, 8.5 10 to the negative 3 equals X. And then, hold on, I did something wrong there. 0.100. Oh, it's not 0.100. It says 1 molar. Sorry about that. Oh, why did I went so fast, and that's what I get for it. 1 molar. Ah, you're like, Vela. I should have kept it that way, but I won't. I better keep it as it's supposed to be. 1 molar. I'm glad I have the answer written on the paper for this one. All right, 1 molar. So there I was, so that won't be the answer then. It'll be 7.2. Oh, it makes the math even easier. So it's 2.7 times 10 to the negative 2. Equals X. Now, X in this case is the H3O. So the pH equals negative log of, that's great how I do the wrong thing on the, I know y'all were yelling at me when I made the video, like, Vela, no, not 0.1, no. Okay, log negative 1.57. Is that it? Yeah, 1.57 is the pH. Okay. Okay, so 1.57 is pretty, is acidic. Now, if I were to add, I'm going to make a change on that problem on, that was part 1, and part 2 just says this. A 42 gram sample of sodium fluoride is added to 1 liter sample of 1 molar hydrogen fluoride. Assume there's no change in volume occurring. Calculate H plus pH. Just calculate the pH and H plus. That'll be good enough. You can get the other things, I know. So, all right, here's what's going on. Instead of having just 1 molar HF, which I messed up there too in my picture, they're going to add to it 42 grams of sodium fluoride. Now, they said they're going to add it to a 1 liter sample. Why are they giving you the volume? Because they want you to know what the molarity of this is, okay? 42 grams of sodium fluoride in 1 liter of solution. Now, they say assume the volumes are additive. You know, if you add some salt, 40 grams of this, it's going to make the level go up a little bit. It'll change the volume a little bit. Sometimes they could say, they can tell you what the new volume is after you add it. In a real lab, you would want to do that. You want to see what the actual volume. But if it's a small amount, it doesn't change it. We can disregard it. It will be insignificant, negligible. All right, so that much is dissolved in 1 liter. So does that look kind of like they want you to get molarity? Now, I'm not going to divide this here, even though it looks kind of that way. So 42 grams. First, I'm going to change that to mole. So let me, eraser is better than using my hand. Okay, grams NaF to moles of NaF. Now, you could be asked to do something like this on AP. 1 mole of sodium fluoride will be, and fluorine is 19 plus 22.99 for sodium, 41.99. All right, so, yeah, 41.99, almost pretty much 42. Look, it's 1 mole pretty much, okay? This divided by that is 1. Oh, that's easy. 1 mole. So the molarity of NaF, initially, when you add it in the very beginning, you put that in water, it dissolves. You have 1 mole divided by in 1 liter of solution. So that's going to be 1 molar NaF. So here's what they're saying. We're adding sodium fluoride into this, and it dissolves. So now you have a solution that is 1 molar HF. It's also 1 molar, it's molar NaF. But what we really care about between sodium and fluorine, think about, like we talked about in the earlier lessons, will any of those affect the system there? Only the fluoride. The fluoride is common. The sodium's going to be a spectator. So if it's 1 molar NaF, it is also 1 molar F negative initially. So what they're telling you is you have 1 molar of that to begin with. In your new icebox, common ion. Fluoride, sodium fluoride, you're adding something that has a common ion with HF. HF, the common ion is F negative. Fluoride in hydrofluoric acid, fluoride and sodium fluoride are common, and so it will affect the HF. So that's really what you're looking at. You look at your acid or your base, and you say, okay, the positive or negative ion is anything you're adding common. And sometimes you can add an acid into that, and in an acidic solution, it would affect the shift as well. Okay, so here we go. So minus X, and we have plus X and plus X. So 1 minus X, X, and 1 plus X at equilibrium. Now I have to erase this to do my Ka. I don't know that I'm going to be asking you this on the homework, okay? So this might be one of the ones that I'm saying, but I want you to see how to do a common ion. How do these values compare to the, no, I haven't done the problem yet. Calculate it. Ka equals H3O times F negative over HF. So we use the same Ka value. It's still hydrofluoric acid. So what you're kind of saying is, how is the fact that we have 1 molar fluoride added to this initially, how is that going to affect what HF does in its equilibrium, the equilibrium of the HF system? And it will. Okay, so it'll be X times 1 plus X is F negative over 1 minus X. But guess what? You still get to assume X is negligible. And then 7.2, 10 to the negative 4 is approximately going to be X. Now look at this on the top. Isn't this amazing? You'll love this math. 1 over 1. So guess what? That is X. 7.2 times 10 to the negative 4 equals X in this problem, which is your H3O. So my pH will be negative log of 7.2, 10 to the negative 4. They call that the pKa, actually. well, it's also it is in this problem the pKa 7.2 to the negative 4, and it's 3.14 is the pH. So, what? Question number, well, it should be 3, but it says 2. How do these values compare? Oh, percent ionization. I mean, you can do that as well. It will be percent ionization, and you can find the OH as well. You ought to know that already. That's all review, and I don't want to go over the same thing too much. But since your H3O that broke off was 7.2 to the negative 4, in this one, divided by the original molarity of the acid 1 times 100. And 7.2 to the negative 4. I didn't do it for the other problem. And it's 7.2 to the negative 4 times 100. Wow, it's very small. 0.072% is the ionization. But let's mainly look at the pH here. I might mention that one too. Back on letter A, part 1. First of all, I'm sorry. All right, take that back. Go to the last question in A. It says, how do these values compare to the values for the solution that's 1 molar? So just saying, compare number 1, A, part 1, and then A that I just did on the board, part 2, we'll say. That should have been part 3. So in A, part 1, when you put it in pure water, the pH was 1.57. So that's pretty acidic. 1 is like acid, and 14 is base, 7 is neutral. So 1.57, that's acidic. Well, when you had the common ion, your pH was only 3.14. It wasn't as acidic. So it stopped. It blocked the shifting of the Le Chatelier shift. It did shift, but not as much. You didn't get as much H3O, not as much acid, not as acidic. Okay? And then the percent dissociation in number 1 was 2.7%. But in this one, it was a 0.072. Well, I didn't even calculate it in the first problem anyway. But, it'd be 2.7, 10 to the 2 negative. Oh, divide by 1. Yeah, that's correct. 2.7, 10 to the negative 2. Seems weird that yeah, I did it right. It's just a small number percentage there. So, it had a lower percent dissociation. And you see that that makes sense because having something that blocks it less can block off. So we don't really need to worry too much about that. All right, that is what is meant by the common ion effect. Now, the next lesson I'll go over is on buffer, and that is something that is much more important than this. This is something that pops up. I mean, you've done gas equilibrium where you had to put a number there initially, and it can happen with acid and base as well. And it's not necessarily a buffer, but this is not called a buffer when you do this, but buffer is the most important common ion effect that you'll see on the AP exam, and I'll have to make that on the next video section. So I know I don't want to feel like I'm wasting your time with it, but this video, yeah, there's not anything really you have to work from this on the worksheet, but it's good to know this. This is a good thing to know. You'll see why in the next problem. And then in the next video, I'm also going to do a couple of things that will not be on the worksheet. Okay, but anyway, that was just 18 minutes, so the next one hopefully will be not too, well, it might be a lot of stuff, but we'll see. All right.